go to this, and let's see if I can switch back and forth. Boom. Let me get my remote fired up. Oh, perfect. Okay. All right, so we are live. I hope everybody is staying warm and that you didn't have too much of an issue with power outages. I guess, I don't know if you can tell on the camera, it's still a little snowy outside here. I'm on campus, obviously. Little bit background or announcements for today. So if you saw, I sent you all a message and I posted a video to the YouTube channel where I went through just some updated announcements for the next couple of weeks. So obviously we didn't meet on Friday because of our inclement weather. What I've done is, so everything up until today is graded. Homework 2.6 is graded and the solution is posted. So you all have that. Homework 2.7, that was the second tension member design assignment. That's due today. And then you're getting your final homework assignment today for the exam. So today we're talking about block shear. That's going to be our last topic before exam 1. On Wednesday, we're going to do our exam 1 review, and then we're doing our exam 1 on Friday. Now, initially, I had that we were going to take the following Monday off, but we kind of already had our day off because we had our inclement weather. That was a makeup lecture anyway, so we're going to consider last Friday as our day off. And Monday, we're going to jump into threaded rod design. Normally, I would put threaded rods on the first exam, but I've decided to just not put that on the exam. And I probably won't put that on exam 2 because it's very akin to bolts and tension. And so, as you'll see, there's so many similarities that it's probably okay to just sort of leave that off, just cover it and then move on. And then on Wednesday, we'll begin our discussion into bolted connections. And we'll be spending a couple weeks just on bolts. So let's get into block shear. So if you remember, we talked about block shear last time that we were together. We didn't get into the math, but I want to, obviously get into that today and get into an example. So block shear is what happens when you have a tension member, connected via a series of bolts. And to be clear, this could happen with welds as well, although we're primarily going to be focusing on bolts. And this is when you basically have a chunk of the member being ripped out. So you can see there's this, connection right here being yanked on, and there's some bolts here. And basically what's happening is this chunk of material is being ripped out. And so that's the block that is ripping out of the section. And then if you look at the mechanics, if you look at the forces, what's happening is if you're yanking on it like this, then, just think about it from a statics perspective. This plane right here, this plane is experiencing tension, okay? So it's just being yanked on. But this plane here is experiencing shear. Okay, it's being sheared on. That steel is sliding against one another. So you have a combination of a tensile failure and a shear failure that causes a block to be ripped out of the connection. That's why we call it block shear rupture. So sometimes a member can fail with along a region with tension along one path and shear along another. And so that's why we call it a block shear. And so in this example, like I have here drawn on this slide, this was the same thing I had on the previous slide. You can see, like here in the previous slide, as is the same with this one, there's 2 shear paths and 1 tensile path, okay? And we've got to be sure that we account for that correctly when we do the math. Sometimes it's possible that we have multiple different regions or multiple different blocks that can occur, and the block with the lowest capacity governs. And I'll look at this member actually here a little bit later and show you how there's probably another block that's more likely to fail. And so we'll look at that here in a bit. Now, when you look at the spec, okay, the spec equation for block shear looks a little jacked up the first time you've seen it. I'll just go ahead and say it that way to be, I guess, slightly humorous. So if you go to section J4.3 on page 16.1-38, and so I hope everybody's going to that. Now, one of the things that you'll find is that we're no longer in chapter D. Chapter D was the chapter on tension members. We are now in chapter J. And chapter J is a whole new chapter of the spec. Remember, each chapter of the spec addresses something unique, right? So chapter D is the chapter on tension members. Chapter F is the chapter on flexure, so moment and beams. We're in chapter J, which is the chapter on connections. And so this is sort of a connection-related phenomenon. So we're starting to dip our toes into chapter J. And I'm going to grab my manual right over here. And if you turn to section J4.3, it's on 16.1-138. I'm going to assume everybody's turning to that now. Just a little bit on the anatomy on chapter J. J2, or J1's the intro. J2 is on welds. J3 is on bolts. J4 is on the connecting elements. So that would sort of be what we're talking about here. And if you go to J4.3, you see this equation. So it's at the top of the page, and it looks a little weird because we have that Rn, the nominal capacity, equals a pile of junk less than or equal to another pile of junk. And it's like, what? That is weird. That is a lot different than just FYAG. That is a much more complex expression. It's really not. So first off, sometimes you're going to see expressions in the spec written like this, where it's, expression 1 less than or equal to the expression 2. And all that is just the spec's way of saying, it's just a fancy way of saying the minimum of those two. So if it was greater than or equal, which you really don't see very often, but if it was, it'd be the maximum of those two. So this is just basically saying that the nominal capacity of a block in block shear would be the minimum of expression 1 or expression 2. And so I've written it sort of maybe a little bit easier to digest, sort of like that. Mr. Adkins.
Yes, I was looking at the equation. Now, it's related to the equation part of the area. Now,
Oh, don't worry. We're gonna delve into that in very significant detail. But go ahead.
well, it specifies in the related to 0.6 force U A and B.
Well, that's the tensile stress, not a force. So that's
Well, the A subscript NB says net area subjected to shear. So
Yep.
Can you calculate the net shear area, or will it be given to us?
No, you're going to have to calculate it. And we're going to go through an example where we calculate all of these. And you'll see what we're talking about here in a bit. And it's not as difficult as you would think. We're actually using all of the principles that we used before. Don't worry, we'll dig into each one of those terms here in a bit. In fact, let me go ahead and skip on over to my next slide. So if you look at this expression, so first thing I want to do is kind of simplify it a bit, okay? If you look at this expression, what I'm going to do is I'm going to take it and I'm going to simplify it a bit. Now, let's all focus on this, okay? So it's the minimum of these two rows, okay? But look at the two rows, okay? We have a term plus UBS, FU, A, and T, and then on the bottom row, there's a term plus UBS, FU, A, and T. So that term is common, okay? So if we're talking about the minimum, really what we're talking about is the minimum of these two plus that, right? Because they're both rows are having that term out. So what I did is I pulled this part here out, and so I've got UBS plus FUA, or UBS, FU, A, and T plus the minimum of those two. And so if you notice the minimum of those two, both of those have a 0.6 added to it. So both of these have a 0.6. So I just pulled the 0.6 out. So does everybody see how we went from basically from the gray box over on the left to the yellow box on the right? It's just taking the expression and simplifying a bit so we don't have to keep punching the same buttons in the calculator over and over again. Everybody good there? Okay, I'm going to take that as a yes. All right, so first off, I want to make sure that we're clear that ultimately what we're computing is a nominal capacity, okay? So when we plug and chug into the yellow box, we get a nominal resistance. We must then adjust that by a resistance factor, which is 0.75, to get a factored resistance that's in KIP. So don't forget the phi value at the end. It's very easy to forget. Don't forget that. Okay, now, we are going to have a bunch of areas that we're going to need to compute because we've got AGV, ANV, AGT, ANT, etc. So the naming is pretty much conventional as to what you would expect. So the AGs refer to gross areas, the ANs refer to net areas. What about the other subscripts? So AGV would be a gross area in shear. ANT would be a net area in tension. So the little v's refer to shear, the little t's refer to tension. So it's pretty easy to figure out what you're computing. Now, if you actually look at the equation, you see an AGV, an ANV, an ANT. You do not see an AGT. There is no gross area in shear, but we have to compute that because in order to compute the net area, we need the gross area. So we've got to compute them all. So I didn't want you to think I had forgotten that. A couple other terms that are unique. So this UBS term, which I'm just going to go ahead and say this, and I actually devoted an entire slide to UBS, and it's almost kind of a waste of time. UBS will be 1 in virtually every single case that we handle this semester, and there's only one case where it really differs, and I'll show you that here in a bit. But it for all intents and purposes, for what we deal with in CE 414, UBS will equal 1. The only thing that's kind of maybe out of left field is this term right here, this 0.6, okay? Now, if I ask you what is 0.6 and you say, oh, that's a factor of safety, that is wrong. That is not a factor of safety, okay? This 0.6 is actually a mechanics-based term that comes up from a very specific formula that we use in advanced mechanics. And I want to kind of explain that first. Everybody in this room, so I'm curious, how many people in here have already had soils, have already had CE 322? Anybody raise your hand or pop on the audio if you've already had soil mechanics? Some of you are probably in it now in geotech, and some of you have probably already had it. For those of you that have already had it, does this look familiar? Does that look familiar? For those of you that have already had it. Well, there's got to be somebody in here that's already had soils. Has nobody in here already had soils? Geotech, CE 322. Have you seen this? Man. Is there nobody in here that's already had soils? You saw it on the FE exam. Okay. Oh my goodness, man. My heart's breaking. Okay. So for those of you that are in soils now, you will see this soon. Okay. What this is a failure criterion. Okay. And so let me explain what a failure criterion is. You start to get a little bit onto the advanced side of things, especially when you're dealing in like 3 dimensions and whatnot. But whenever you have an element that's under stress, right, you could pretty easily define when that element's going to fail if it's only experiencing one stress. So if you have an element that you're pushing in compression, you could probably say, well, it'll fail when that compressive stress equals a certain value. But what if it's under stress and it's being sheared and it's being twisted, or, you know, if it's got multiple things going on? Well, what we need to do is define a failure criterion. Everybody, if you're in, it looks like most of you are in geotech right now. If you're in geotech, you will see that equation at some point in that class. I guarantee it. That is the Moore-Coulomb failure criterion, and we use that. Moore-Coulomb is appropriate for brittle materials like soils. In fact, you could probably also use it for concrete. We have some other yielding criteria we use for concrete, or failure criteria we use for concrete as well. But Moore-Coulomb is a very famous one that students are usually exposed to, and it's appropriate for soils. And so the idea is you sort of plot your Moore circle, and based on your stress state, you're trying to determine whether or not your element has failed or not. And it's basically a plug and chug expression. For metals, we don't use Moore-Coulomb, we use the von Mises criterion. Okay. The von Mises yield criterion looks like this in 2 dimensions. This is what the equation looks like if it's in 2D. You don't need to memorize that. I'm not asking you to memorize that. So please be clear on that. But I want to show you how it works. Okay, so let's say you have a piece of steel and all you're doing is yanking it in tension. Okay, so if you have a scenario where sigma x is some stress, and then sigma y is 0 and tau xy is 0, then what you would do is take sigma x, set it equal to some stress, take everything else, set it equal to 0, and then it yields when the stress hits Fy. And I think that makes sense. If you have a piece of steel and it's in tension and you yank on it, when does it yield? When the stress equals Fy. That's pretty easy. But the reason why this is relevant is what happens when you take a piece of steel and you shear it. Okay? So what happens when I do this again, but I say, let's take all the normal stress and set it equal to 0, but let's keep tau xy. Let's put some shear stress on there. What happens when we're shearing it? When does it yield? Well, what do I have? 0 squared minus 0 squared plus 0 squared plus 3 tau squared, or tau times the square root of 3. So in other words, it yields when the shear stress equals Fy over the square root of 3. Now, if you take 1 divided by the square root of 3 and plug it into your Casio or your TI or whatever, 1 over the square root of 3 is about 0.577, something like that. And so the steel industry says, oh, what the heck, let's just round that up. And so they round it up to 0.6, okay? Throughout this semester, we're going to see that 0.6 pop up quite a bit. Anytime that there's an element subjected to shear, that 0.6 is either hidden in the material quantity, especially in the specification. Anytime that you have an element subjected to shear, it yields when the shear stress equals 0.6 of Fy. So whenever you see a shear term, that's where that 0.6 pops up. Look at the if you look at the equation here, look where the 0.6 is. It's multiplying all the terms that are related to shear, not the terms that are related to tension, okay? And so there's an explicit reason for that, and it all goes back to this yielding criterion. I'm not expecting you all to be masters of advanced theoretical mechanics. I just want to make sure you kind of understand what I'm talking about here. Does this make sense? Anybody have any questions? Everybody good on this? All right, I'm going to assume everybody's good. Okay, now a couple other things. I skipped over this term UBS. So UBS is kind of like a shear lag factor. It accounts for non-uniform stress distributions that you get around the failure block. And I want to be clear, when I say most cases, I really mean like 99% of cases, UBS is 1. And we won't deal with any other cases this semester. There is one instance where UBS equals 0.5 though, and so in professional practice land, I kind of want to make sure that I'm explaining this. So let's say that you have a beam in a building. So here's the. Oh, let me get my pen color, something that's a little easier to see. Let's say you have a floor slab, right? And you have, here's Dr. Mike standing on the floor slab, right? And what you've got is you've got a floor beam that sort of frames in. So there's a floor beam right here and a floor beam right here. And you have a floor beam that also runs this way. But what you want is you want the tops of the floor beams to be level. So what you do is you cut like a little nubbin out of the top of that floor beam on each end. So you can see where that's been happened, like right up here. You can see that they cut this little nubbin out, this little region right there. You cut that little nubbin out so that when you frame the floor beams together, that they sit flat, okay? And so we have a name for that. We call it a coped beam. So whenever they cut that little nubbin out, it's so that when beam A frames into beam B, that the top surface is flat, so you can put a slab on it and everything sits flat. Now, what you might be interested in doing is if you have a coped beam, here's the coped beam, here's the beam, there's the beam, and you've got bolts like that, you might be interested in, I don't know, computing the block shear capacity of that, right? And so whenever you have multiple rows like you do here, UBS is 0.5. If you ever have an instance like what's going on up here up top where it's just a single row of bolts, then you take UBS to equal 1. So this is the only instance where UBS is a different value. I almost feel kind of bad that I'm devoting so much time to talking about it. I just wanted to, give you a taste of things to come in professional practice. All right, any questions? You like my term nubbin? Nubbit? Little nub, little chunk. That is a technical term, mind you. You will find that in the technical literature, I promise. All right. Hey, you get the real deal with me. Okay. I get the reference. I actually get the reference. That's a good one. Okay. All right. So one of the things I had mentioned in at the earlier part is that you might need to identify multiple potential paths. Like, for example, on this plate, you could have this central block rip out. You could also have the block over here on the right rip out. Now, when I investigate block shear paths, what I want are paths that leave all the bolts intact, that completely separate the member from the connection, and they have to include a path that's subjected to shear. In other words, like if you had a member like this and you had bolts, somebody might say, well, wait a minute, Dr. Mike, why don't we just consider this path? Like, what about that? Why can't we do that? Well, that path doesn't have anything associated with shear. That's just a tensile failure. That has nothing to do with block shear. That's just net section fracture. So there's no block failure where there's a shear component. There has to be a shear component. So you have to have a member inside the member. So we have to leave all the bolts intact, and we have to separate the member from the connection. So assuming everything's symmetric, I'm proposing that these are two possible failure paths. And what I'm getting at in terms of the mechanics is, if we look over here on the left, all of this path is subjected to shear, and all of this path is subjected to shear. And then this path here, this path is subjected to tension. So in order for the member to fail, all that has to rip out. Okay? Now what about over here on the right? Well, this is the only path that we see here in shear. For tension, we've got this. Actually, I can do a little better now. So this is my tensile path. So if I look at these two paths and I ask myself which one would govern, well, assuming everything's to scale, I'd probably think that this one would happen first, because there's less steel that it's ripping through. Remember, this is just a free edge. It's just hanging out there in space. It's not sliding against anything. So this path over here on the left has less material that it's ripping through. It's probably going to govern. Whenever you're selecting failure paths, you have to ensure that you're picking a path that makes sense. For instance, this is very akin to the problem that we're going to do today. And so we've got a connection of these 8 bolts here on the bottom. And I'm proposing that the block that would govern would be the block that you see here, this one that's in orange over here on the bottom. Because the alternative would be, well, instead of this little block here, it's ripping through all of this, like all this over here. And if I'm thinking path of least resistance, what's the smallest potential block that would cause this member to totally separate? And it would be this one, because if I look at it on the top, really what we're having is something like that go on. And so it's just sort of sliding off from that connected face. Does that make sense? Okay, good deal. All right. So what we're going to do is we're going to look at this problem. So this is an angle. So, we've got an angle that sort of, goes like this. and we've got bolts like that and bolts like that. And so we're going to investigate the block shear capacity of this particular connection. All right. So it's an L6 by 4 by 5/8, and it's of A36 steel, and we have 1-inch diameter bolts. So we're going to determine the design capacity according to block shear. So if everybody's good, I'm going to go ahead and transition to the notebook here. Let me pull the notebook up. There we go. All right. I'm going to give everybody a sec to write all this down. If anybody wants to write anything down, I'm going to give everybody a sec. But as we're going through this, does anybody have any questions? Now, one thing I will tell you about this problem, and it is because it's an angle, we actually are not going to need any of the properties for the L6 by 4 by 5/8. In fact, the only thing we're going to need is the thickness, and the thickness is 5/8 of an inch. If this were a channel, or if this were a wide flange or something like that, like a W shape or a C shape, then we would need a flange thickness or a web thickness or what have you. But because it's an angle, the nice thing about angles is the thickness of that leg is 5/8 of an inch. So just so everybody understands the three-dimensionality of what we're doing here, so we've got an angle that sort of goes off into the distance like this, and we've got, you know, holes like that. Like this is kind of what we're looking at for this problem. Okay, everybody good there? Now, we've got some properties, though we do need, to know what's going on with A36 steel. Somebody tell me, what do we need from A36 steel? Well, what can we look up for A36 steel? The FY and the FU, and so what is the FY and the FU for A36 steel? There we go. That's what I like to hear. Okay, so what we can say here, I'm going to move this. All right, so A36 steel, and this is table 2-4, states that FY, I heard some beeps there. Let me write this down. I'll get to KSI, and FU is 58 KSI. Yeah, it's page 2-48. We've got some teamwork in the chat. I like it. I like it. All right. The other thing that we know is we know that the bolt diameter is 1 inch. So therefore, the hole diameter is 1 1/8 of an inch, or 1.125 inches. Okay. All right. So let me cheat a little bit. Okay, so I'm going to copy this down here. All right. Now, is everybody okay with the failure block that I've indicated? So I think that the failure block is going to look something like this. This is the section that I think is going to rip out. Everybody okay with that? Okay. All right. So let's sort of hatch this in. Okay. Now let's recognize a couple of things. Okay. This is the shear path. This is the tension path. Okay, so let's take the shear path first. Okay, let's calculate some areas. So we need gross areas and net areas. So we're going to start with gross area and shear. Okay, by now we should have enough understanding of gross area and net area that I'm hoping that we can compute the gross area in shear fairly effectively. Let's keep in mind, note that we have a 5/8 inch thick angle. Let me make sure that I get that right. Yes. So how are we going to compute the gross area in shear? Somebody tell me how we're going to do that. Well, not just the length of the bolts, but the length of that path, okay? Because what we're looking at here, I want to make sure I do this maybe a little three-dimensionally, so hold on. I'm making a mess here. So here's the angle, and the failure block that I've indicated sort of looks like this. Okay, and what I'm talking about as the gross area in shear is I'm talking about, like, keep in mind, okay, so here's the angle, and I'm yanking on the angle, I'm yanking on the angle like this, okay? So what path is experiencing shear? Well, it's going to kind of be this right here. That's the gross area in shear, okay? The gross area in tension is going to look like that, okay? So now you're jumping ahead on net area, Gordon. I'm talking about gross area first. That you're getting on. No, you're fine. But let's handle gross area first. Somebody, I've got some discussion in the chat, but I want somebody to tell me the number, like what it's going to be. You know, the thickness times what? What's the number? Like, what is this length? It's 10. There we go. All right. So it's going to be, and so if you want, you could say 10.5 inches times 5/8, because this dimension right here is 3 plus 3 plus 3, which is 9, plus 1.5 is 10.5 inches. So 10.5 times 5/8. Okay, so somebody tell me, what is 10.5 times 5/8? Y'all got handy dandy calculators? I'm breaking out the Blues Clues stuff again. Handy dandy. There it is. $6.56. All right. 6.5. We'll just say 6.563. That's close enough. Okay. Now, everybody okay with that? Now, if you're okay with that, before we get into tension land, we've already got a gross area. Now let's talk about a net area. Okay, so we got the gross area in shear. Let's talk about the net area in shear. Now, as Mr. Blizzard said in the chat, he's absolutely right, we have the gross area minus the area lost due to the presence of bolt holes. So how do we determine the area of a hole? It's the same as before. The diameter of the hole times the thickness. So it's going to be the gross area minus some term, however many holes, the diameter of the hole times the thickness. The $64,000 question is, how many holes do we subtract from the gross area to get the net area? Keep in mind, we're talking about the gross area and the net area in shear. So your eye should just be focused on that long horizontal path. How many holes are we subtracting from that path? Talking about this path right here to get that. Mr. Blizzard's right on the money. It's 3.5. Because we do 1, 2, 3, but this is not a full diameter. That's a half. So it's 3.5. That's exactly right. You subtract 3.5 bolt holes. So this is 6.563 square inches minus 3.5 times 1 1/8 or 1.125 times 5/8. Anybody have an answer for me on that one? $4.1. Okay. I'm gonna give it a little bit more specificity. I'm getting 4.102. Is that what you're getting? Like if I take it a little bit further? I'm just doing that. I probably wouldn't do that in practice. I just want to make sure that when you all are doing the math on your own that you could see, okay, I got that number too, so I know it's the right number. Like 4.1, it's one of those numbers that's not specific enough, you know. So in the education side of things, I'm taking it a little further. Okay. Now, okay, let's keep on with this. Now let's do AGT. Sorry, AGT. Yeah, emphasis on the T. Now we need to do the gross area in tension. Okay? So help me out. How are we going to compute the gross area in tension? What's the formula going to be? So it's still going to be a length times the thickness. And I'll go ahead and tell you the length or the thickness is still 5/8. Boom. Mr. Riggs got it. It's 3.75 because what we're talking about is we're talking about that dimension right there, which is 2.5 plus 1 1/4 or 3 3/4, 3.75. And so what is 3.75 times 5/8? What are you getting? Let's do 3 decimal places again, just to make sure that we're all getting the same numbers. Again, I probably wouldn't be that specific in real world, but 2.344. All right. Now, I want somebody else in the chat. I've seen a lot of people respond. I want somebody else, somebody who hasn't responded. Okay. ANT is going to be AGT minus some degree of holes or some number of holes, diameter times the thickness. Somebody that hadn't responded yet. How many holes are we going to subtract from the gross area in tension to get the net area in tension? Boom. 1.5, right? Because we subtract 1. Oh. Man, I'm backwards today. And then half. Right? So 1.5 holes. All right? That's exactly right. So this is 2.344 square inches minus 1.5, 1 1/8, 5/8. All right, so what do we got here? We've got minus. All right. Anybody got a number for me on that one? 1.289. All right, and that's what I got as well. Okay, now just to be clear, UBS is also 1. Again, we're never going to have a problem in this class where it's not going to be 1, so I'm just going to go ahead and put that down. Okay, so let me get over here. Let's scroll down a bit, and let's just sort of summarize some values here. So AGV, ANV, AGT, ANT. So 1.289, 2.344, 4.102, and 6.563. We had FY is 36, FU 58. And while we're at it, UBS is 1. Okay, so these are all the inputs that go into our expression. Well, actually, one of them's not needed, but but you'll see why. Oh, didn't mean to do that. Sorry. Hold on. Okay, so here's our expression for net area, or for block shear. And again, the expression looks nasty, but if you have all the inputs, it's very plug and chug. So it's UBS, FU, ANT, sorry, that was not supposed to be equals, that's plus 0.6 times the minimum of FY, AGV, or FU, ANV. So we need basically a tensile fracture, but either a shear yielding or shear fracture, whichever one governs. And so we just start plugging it in. So we have 1.0, 58 KSI. ANT was 1.289. As I'm writing this, if I have a number that's off, let me know. Plus 0.60 times the minimum of, let's see, 36 KSI and 6.563 inches squared, and then 58 KSI times 4.102 inches squared. Okay, now in order to ensure that we're following along, okay, I need some help from the chat. Okay, so first off, could somebody just do that? What are we getting for this value right here? Just that part. So I'm getting 74.76. No, it's fine. Here, I don't think I did the best job of indicating that was a decimal. So that we'll share the blame on that one. Okay, so 74 point. We'll just say 7. Hey, you know what? This is block shear. Let's just say 74.8. 74.8 kips plus 0.60 times the minimum of. Now, what we're going to do is let's do each one separately. So let's do that one and then that one. So the first one, 36 times 6.563. 236.3, and then 58 times the 237.9. Okay, and I'm getting those as well. So save on space a little bit there. Okay. So of those two, we're taking the minimum. So we're obviously going to take the one that's on top, right? Of those two, that one's the smallest. So 74.8 plus 0.60 times 236.3 kips. And what do we got there? $216.6. Do I have a second on that? All right. So is that the answer? Or am I missing something? There you go. Don't forget the phi value. This is a very easy thing to forget, that you go through this big old expression, but you forget that we're not interested in nominal capacity. This is LRFD. We're interested in design capacity. 0.75 times this. And so times 0.75, I'm getting that phi RN is 162.4 kips. That's the phi value. Phi is 0.75. See, all this RN, see that 216.6 kips, in the end, that's RN, right? Because RN was all that pile of junk. In the end, we want phi RN, so we have to take that RN and multiply it by phi, which is 0.75. No, that's a fair question. That's a fair question. Now, while we're sort of messing around here, I want to see if anybody has any questions. Now, one thing that is interesting to do, and I'm not making you do this, but you ought to take this member, because you've got everything that you need to compute gross section yielding and net section fracture. You ought to see, okay, we've got phi RN. That's its capacity under block shear. What about its capacity under gross section yielding, the 0.9 FYAG? What about the 0.75 FU times net area times U? What about going through and doing all of that and seeing, well, what about gross section yielding and net section fracture? Is this the lowest? Maybe it is, maybe it's not. I'll give you an example. So here's just a note. Gross section yielding is 0.9 FYAG. If you do that for this angle, you get 189.9 kips. So without doing the block shear one, or without doing the net section fracture one, we could tell that gross section yielding isn't going to govern. If I yank on this angle, it's going to reach its block shear rupture capacity well before it reaches gross section yielding. Maybe that's also true for net section fracture, in which case this angle is actually governed by block shear. That's very possible, and it's worth checking into. It really is. Before we call it, I do want to just sort of pull up your homework just to sort of show you what it looks like. So this is your homework. If I could drag it over here. So I want you to determine the design, or the block shear rupture capacity of this Okay? And the big thing is to make sure that you're accounting for the material properly, because if you look at the, and I showed you this last time, but if you look at the block shear rupture capacity and you look at the failure case, really what you're talking about is this, right? So what you ought to do is see if you could compute the capacity of a single one of those blocks, and then recognize that it takes 4 blocks to fail the entire section. And so if you could recognize that, then this is going to be a pretty straightforward problem. So I would try and compute Rn for a single block and then multiply it by 4. You could try and account for all of them together, but I think that'd probably be kind of difficult. So does that make sense? Any questions on that?
Dr. Mike. So
yes, sir.
Once we, so like you said, you solve for 1 and then you multiply by 4. So one of those is going to be the same for all the other 3.
Yeah. So like if you rotate it, I mean, they all kind of, oh goodness, they all look the same, you know, like they're all the same, you know, connection scenario. They're just repeated, you know. So any one of those blocks are going to have the same capacity. I like it. Any other quick questions before we call it?
Yeah, I got a question.
Yes, sir.
If one of those blocks fails, does that make the other ones more likely to fail because the load's distributed differently at that point?
That's a fair question. You're getting into like indirectly into an interesting topic in bridge engineering about redundancy. The idea that if a member fails, how does the load shift around the rest of the system? What I'd say for this is that really the cumulative capacity of this section in block shear is the capacity of all of those. And you probably wouldn't find a scenario where one of the blocks would fail without the others. But if there was a flaw and one of those blocks were to say maybe, you know, fail, that would cause such a dramatic increase in load and all the others that they probably all fail at the same time. So I think for practical purposes, looking at it member by member, we can just assume that, you know, the whole thing's going to fail all at once.
Okay.
Any other quick questions? I know some of you might have class at noon. All right, well, I'm going to go ahead and call it. Everybody stay safe. You know, only drive if you need to. Stay warm. Hope everybody is doing well. And assuming we don't have any major weather issues, I will see you on Wednesday. This is the last topic on the exam, and so we'll do our exam review on Wednesday. That's all I've got. I will see you then. Yes.
In the event either of us don't have internet on the exam, what's our plan on that?
We'll talk about that on Wednesday. We'll figure something out. I'm not gonna, you know, I'll make sure you all aren't disadvantaged. I promise.
Well, on Thursday this past week, I had power but no internet, so
We'll figure something out. Don't worry. I promise. I won't leave you hanging. All right. I'm gonna stop the recording.